So, we had seen the relation between angular momentum of a rigid body about some point and the angular velocity of the rigid body if it is rotating about some axis. So, and the relation was L is equal to I omega, but then this was a vector, this was a vector, and this was a tensor of rank 2. We call it tensor of rank 2. It has 9 components. It has 9 components with respect to some x, y, z axis chosen. This is a vector. This is a vector, and this multiplication here is like a matrix multiplication. We had this moment of inertia tensor, which is I x x, I x y, I x z, I y x, I y y, and I y z, and then you have I z x and I z y and I z z, with I x x equal to summation over I m I y I square plus z I square, and similarly I y y summation over I m I, and then x I square plus z I square, I z z as summation over I m I x I square plus y I square. These moment of inertia are like moment of inertia as we studied in class 11 about x axis, about y axis, and about z axis. But then there are other terms which are known as products of inertia, I x y, which is same as I y x, and that is minus summation I m I and then x I y I. Take ith particle, see what is the x coordinate of that ith particle, see what is the y coordinate of that particle, see what is the mass of that particle, multiply. Do it for all the particles of that rigid body and add. That is this I x y, which is same as I y x. In the same spirit, I y z, which is same as I z y, and that will be minus summation I m I and y I z I, and the last one is I z x, which is same as I x z, and this will be minus summation I m I and z I x I. These are called products of inertia. And this L vector is here L x, L y, L z, this column, and here it is omega x, omega y, and omega z. And the meaning is that L x is equal to matrix multiplication, this into this plus this into this plus this into this, that is I x x omega x plus I x y omega y and plus I x z omega z. So, I x z omega z, and similarly L y and L x. L y will be this will be I y x omega x. So, I y x omega x plus this I y y omega y. So, I y y omega y plus this I y z omega z, and L z will be this row. So, I z x and omega x plus I z y omega y and plus I z z omega z. And in general, L is not parallel to omega. The angular momentum and angular velocity are not parallel in general. So, let us take an example. Let us take an example, and example is that I have a rectangular plate, say uniform rectangular plate, this plate, and then this is the origin, and let us say let us say it rotates about this axis, and therefore, this is omega vector, this is omega vector is in this direction. So, this whole thing is rotating about this line, and length is L here, width is B, the total mass of this is capital M, and here is the origin, and I take this as the x axis, this as the y axis, and then z axis is perpendicular to the plane. So, what is the kind of situation? I have let us say this is that rectangular plate, and here is a corner, and I am taking x axis. So, here is x axis, I am taking y axis in the plane of this plate. So, in the plane of this plate, this is x axis and this is y axis, other edge, and z axis is perpendicular to this plane. So, z axis is here, z axis is perpendicular, this is z axis, x axis, y axis and z axis, origin. So, this is the kind of thing, and it rotates about y axis, that means it rotates like this, with a uniform angular velocity omega. Okay. So, that is the kind of situation, and what we need is angular momentum of this rigid body, and for that what I need this moment of inertia, this 3 by 3 9 components, and then omega we will write, L we will write, and we will calculate that. So, let us first calculate moment of inertia. This is O, moment of inertia about O, about the origin. Now, we are not saying about an axis, not about a line, it is about a point, and of course, to get those 9 components we need some x, y, z axis. So, here is x axis and y axis and z axis. So, let us calculate, Ixx. What is Ixx? What is Ixx? Ixx is moment of inertia, usual moment of inertia about the x axis. So, here is the x axis and here is the plate, and you know what it is, it will be m times b square by 3, correct. If you have a rod of length b and you need it about this line, it is mb square by 3, and same is the formula if you extend it around the axis. So, this is mb square by 3, and similarly Iyy, which is moment of inertia about y axis, here is y axis. So, if this is a rod, it will be ml square by 3, and if you extend it this way, it remains ml square by 3, and Izz you can use theorem of perpendicular axis, it is b square plus l square. Okay. So, that is very simple, that you have done several times in your schools. Now comes the other factors, Ixy. What is Ixy? Here Ixy equal to y, Iyx is equal to minus I mixi yi. So, we define Ixy as minus summation over I mi xi yi, and for continuous bodies you do not have particles, separate particles. So, you cannot do this summation, this is integration dm x into y. So, you take an element here, some dx dy, small element, see what is the mass here, what is the x coordinate, what is the y coordinate, multiply. So, mass here is dm, x coordinate is x, y coordinate is y, so multiply, and then this is x into y, What is dm? dm is capital M divided by AB into dx dy, right. This is dxy, this is dx, and this is dy, and this area is dx into dy, total mass is m, total area is b into L. So, this is m divided by b into L. So, this is mass per unit area, and then area here is dx dy. So, it is this, and what are the limits? Let me separate. So, m by lb is constant, then you have x dx and y dy. X will go from 0 to L. So, x will go from 0 to L. You have to take this element here, everywhere, and then add, and y will go from 0 to b. So, y will go from 0 to b. integration is fairly simple. It is m divided by L into B, L square by 2, B square by 2. So, m into LB and divided by 4, that is Ixy and same as Iyx. Okay. This is same as Iyx. And what is Iyz? In Iyz you will have Mi, Yi, Zi, and Zi is 0 for all particles. Z coordinate is 0. Okay. This whole thing is in xy plane. So, this Z is 0 for every particle of this plate, and so this is 0. Z is 0 for every particle of this plate, and therefore, this is also 0. So, the only product of inertia terms are Ixy and Iyx. So, let me write the moment of inertia tensor. So, that moment of inertia tensor is Ixx. Ixx is here, m b square by 3, Iyy I have to write here, m L square by 3, and Izz I have to write here. So, m by 3 and then L square plus B square. Then Ixy, this Ixy, and Ixy is negative, yeah, negative. So, minus m L B by 4 minus m L B by 4, and all others are 0. This is 0 here, this is 0 here, this is 0 here, and this is 0 here. This is the moment of inertia of this plate about this origin. These are the components of moment of inertia along or with respect to these directions x, y, and z. But remember, a vector has 3 components, but components can change if you rotate the axis. If you change the axis, if you are using some x, y, z axis and then you rotate the whole axis system just by some angle alpha, say some angle alpha z, about z or about any line, you rotate and say this is x prime, this is y prime. You write the component of the vector along or in the directions of this x prime, y prime, z prime, the components will be different. If you are using x, y, z axis, there are some components of a given vector. If you are using x prime, y prime, z prime, the components will be different, but vector is not different, it is the same vector, it is vector, it is a physical quantity. Similarly, here I have chosen one particular axis system x, y, z. Of course, I need moment of inertia about the origin, about this given point, this I cannot change, but I could have taken some other axis, the x prime here, y prime here, and z prime. Then these components will be different, but that does not mean that the moment of inertia of the plate is different. Moment of inertia of the plate about O is a physical quantity, and that physical quantity is expressed in components once you have chosen x, y, z axis. If you choose different x, y, z axis, the components could be different, but moment of inertia as a physical quantity will remain same. In fact, tensors and vectors, these are defined in terms of this transformation. If you rotate the axis by certain angle, the relation between new components and the old components of the same physical quantity, there is a certain rule about according to which these components and those components will be related, and if those transformation equations are obeyed, then only we say that this is a tensor of rank 2 or this is a vector which is also called tensor of rank 1. And in the matter of fact, as a matter of fact, scalar is also a tensor of rank 0. So, you have tensor of rank 0 which is scalar, tensor of rank 1 which is vector, tensor of rank 2 which is like this, then tensor of rank 3, 4, 5, no special names are given. So, that is it. So, this is our moment of inertia tensor components, and we are interested in the angular momentum. So, what is omega? Omega is along the y axis. So, omega, this is our moment of inertia. So, omega we will write omega x, omega y, omega z. X component of omega is 0, y component of omega is omega, and z component is 0. So, this is our omega, angular momentum vector. This is moment of inertia tensor. And when you do this multiplication, matrix multiplication, what you get is your angular momentum vector, Lx, Ly, Lz. So, what is Lx? Lx is equal to this into this 0, this into this, minus m L b by 4 and then omega, and this is plus 0 into 0 is 0. So, this much I cap, this is Lx, fine, this is Lx. And then Ly is, what is Ly? What is Ly? Ly is this row, Ly is here, therefore, this row and this column. So, this into this 0, this into this, yes, m L square by 3 omega, then this into this is 0. And what is Lz? This is Lx, this is Lx, this is Ly, and Lz is 0 into 0, 0 into omega, and this quantity into 0 is all 0. So, this is 0, this is Lz. So, that means L is minus m L b omega by 4 I cap plus m L square omega by 3 and this much omega, that is j cap. Okay, this is it. So, this is L vector. Omega was omega j cap. You can see that L is not parallel to omega. L is not parallel to omega. L is not parallel to omega. Let us take another example. The same story, the same system, the same plate, but this time let us rotate it about the z axis. So, that means, if this is a plate and if this is x axis, this is y axis and this is z axis, it is rotated about this z axis. So, it will rotate like this with some uniform omega. Okay. So, this is z axis and it will rotate like this. Previously, we had this as the axis of rotation, y axis, and it was rotating like this. So, only change we are doing, same origin, but now the omega is along the z axis. So, plate is going like this. So, let us do for that. So, let me make some space. I think I can make the space this side. So, let me have the same figure, and omega is not here, omega is now about along the z axis. So, this is z axis and omega is in this direction, it is going like this. I want angular momentum of the object about this point, and I will use the same procedure. Now, moment of inertia of this plate about this origin is a fixed quantity, wherever is omega vector, that does not matter, right. Moment of inertia of this is given by all those Ixx, Ixy, Ixz, and in that omega does not come, omega comes later, Moment of inertia, as long as that point is fixed about O, is the same moment of inertia, and therefore, the same moment of inertia will be there. In fact, I can work there itself, I can work, or let me write, it is the same moment of inertia, it is m b square by 3 and then minus m b L by 4 and then 0 here, minus m L b by 4 here, m L square by 3 here, 0 here, then 0 here and 0 here, and m L square plus b square by 3. So, it is the same moment of inertia, but omega is different. Omega is now in z direction. So, omega x is 0, omega y is 0 and omega z is z. So, this is 0, 0 and then omega. So, that is the difference. Here it was 0 omega 0, this angular velocity vector was in the y direction, here this angular velocity vector is in z direction. So, see how much is this Lx, Ly, Lz, Lx, Ly, Lz. What is x component? What is Lx? Lx is this into this 0, this into this 0, this into this 0. So, no Lx, Lx is 0. So, Lx is 0. Ly, Ly, so this into this 0, this into this 0, this into this 0. So, Ly is also 0. Lz, Lz is this into this plus this into this plus this into this. So, this is m, L, m and then L square plus b square divided by 3 and then omega. So, L is m L square plus b square by 3 and omega vector, because your omega is only in z direction. So, omega is omega and k cap, right, and this is also Lx is 0, Ly is 0. So, Lz this k cap and omega k cap is omega vector. So, you have this relation. Yes, L is parallel to omega and the magnitude L is equal to I omega. That is simple class 11 moment of inertia. Okay, about this, what is the moment of inertia about the z axis? Use perpendicular axis theorem and here it is. This is the moment of inertia about z axis. So, L equal to I omega, torque is equal to I alpha, all those things can be applied in this case. The same plate, the same origin. But if the rotation is about this y axis, no, you need product of inertia and L is not parallel to omega and things are very complicated. But if the axis of rotation is z axis, very simple life. So, what is so special about this z axis which is not there in the y axis? And there comes the concept of principal axis of the system. If you have any rigid body and you are given a point fixed in that rigid body or with respect to that rigid body, from that point you can definitely find 3 perpendicular directions, at least one set of 3 perpendicular directions in which the product of inertia terms are 0. So, if you use those 3 axes, very special directions in the rigid body, once the rigid body is given and a point is given, origin is given, you can obtain at least one set of 3 perpendicular directions. So, that if you choose those directions as x, y, z axis, the moment of inertia tensor, that matrix, will not have product of inertia terms 0, those will be 0, only the diagonal terms will be there, I x x, I y y, I z z will be there. Now, it so happens that I will talk more about these principal directions, but it happens that from this O, one of those 3 directions is the z axis. One of those 3 directions is z axis. X axis is not one of those 3, y axis is not one of those 3, but z axis is one of those 3. So, where are the other 2? Z axis is a principal axis direction, it is a principal axis for this plate. Z direction is the direction of principal axis for this plate. Where are the other 2? They have to be in this xy plane, but these are not, because if I use these x, y, z, I do have this product of inertia terms. You can find that and this will be your homework. It must be in this plane. So, suppose it is at some angle alpha, this is say x prime and this is y prime in this plane. So, if these are principal axis, then the product of inertia term should be 0. So, take this as axis, x axis, take this as y axis and the z axis is here, and calculate these terms as I had calculated from the very basic definitions. I x y is equal to minus summation I m I x I y I. Calculate that product of inertia, put that equal to 0 and find what is alpha. Then you will get those three principal directions, but nevertheless at this moment if the axis of rotation is, what is axis of rotation? Direction of omega, that is direction of omega. Remember, this need not be constant in time, it can change with time. I am talking of certain instant. The direction of omega is along one of the principal axes. Then you have L is equal to I omega, where I has the usual meaning moment of inertia about that omega direction, about that axis, instantaneous axis of rotation. So, this will work provided this omega is along one of the three principal directions, and here it so happened that yes, the z axis was one of the three principal directions, and therefore this all worked, and here it was not, and therefore you had all those complicated things. Now a question, if you look at this L, I am now rotating this plate about this y axis, x axis, y axis, and this is the direction of omega. I am rotating it this way. So, all these calculations are valid. Angular momentum is given by minus m L b omega by 4 I cap plus m L square omega by 3 j cap. My question is torque 0 or it is not? Torque, remember torque we say is dl dt. So, if this L is constant in time, as time passes this L remains the same, then the torque is 0, all right. The question is, in this condition what happens to that torque, is it 0 or it is not? Lx, see this Lx, this is Lx, x component of L, and that is capital M constant, mass of the plate, small l constant, length of the plate, b constant, width of the plate, omega say constant, it is rotating at uniform velocity. I give you this plate is rotating about this y axis with a uniform velocity omega. So, this omega is same, is does not change with time, constant. So, this Lx is constant. Come to Ly, m is constant, mass, L square constant, omega constant, 3 constant, Lx is constant, Ly is constant. So, what is the conclusion? This L vector is constant, and so what can we derive? If L is constant, the torque is 0. For uniform angular velocity of the plate, you need not apply any torque, but this conclusion is wrong. This conclusion is wrong. Lx is constant, Ly is constant, Lz is constant, but the torque is still not 0. Why? Because this I cap, this j cap is not constant. As the plate rotates, the x axis was along the length, all right. So, if this is the plate, this is the x axis along the length and y axis is here. This I cap is in this direction along the length and j cap is in this direction along the width, and as this rotates, this j cap does not change, but I cap changes. This is I cap now, and this is I cap now, and this is I cap now. So, as it rotates about the y axis, this j cap remains constant, but this I cap changes. So, although Lx is constant, Ly is constant, but what we are using is a rotating frame of reference. K cap is also changing. Where is K cap? Perpendicular to the plate. This is z axis, and as it goes from this position to this position, z axis also tilts. So, K cap is also changing. So, we are using rotating frame of reference, non-inertial frame of reference. In this reference frame, yes, with these x, y, z axis, yes. In this rotating frame, L is constant, but if in the rotating frame L is constant, that does not mean that dl dt equal to tau will be 0. So, we had this relation, very important relation, dl dt in the inertial frame is equal to dl dt in that rotating frame and plus omega cross L. So, in our case this is 0. In the rotating frame this L is constant, but in the inertial frame, which is non-rotating, dl dt is equal to omega cross L. You have expression for L, you have expression for L, you have expression for omega. You can calculate from here what is the torque. So, let us do that. Let us do that. Simple. Torque is equal to omega cross L, right? Torque is equal to, this is torque, inertial frame of reference, dl dt is torque, is equal to omega cross L, is equal to omega cross L, is equal to omega j cap and then cross L, this L here, minus m L b omega by 4 I cap, and then minus plus here m L square omega by 3 j cap. Cross product j cap cross j cap is 0. So, you have minus m L b omega square divided by 4 j cap cross I cap is minus k cap. So, plus here and k cap here. This is our torque. To maintain uniform angular velocity of this plate, you have to apply this much of torque. So, torque equal to I alpha will not work. Alpha is 0, no angular acceleration, the angular velocity does not change with time, neither the magnitude nor the direction, but torque is not 0, angular acceleration is 0, torque is not 0, torque equal to I alpha will not work. To maintain a uniform angular velocity, you have to apply this torque, you have to apply some forces in the xy plane perhaps, which will produce this kind of torque in z direction. So, those are the kind of things that are there. Now, how to find this principal axis of any rigid body given the origin? So, there are standard mathematical procedures. You have to solve certain equations, and those equations will definitely give you the 3 directions which are principal directions or principal axis direction or principal axis going through that particular origin. But there is a, if symmetry permits, if the object is of some good geometrical shape, you can just by inspection find where are those principal directions. So, there are 2 simple rules which works most of the time. I will tell about that. So, one is rotational symmetry axis. We call an axis as n-fold rotational symmetry axis if if a rotation of 2 pi by n, of course n is an integer, positive integer. If a rotation of 2 pi by n about the axis does not change the mass distribution of the body, all right. So, this is called n-fold rotational symmetry axis. If you rotate the whole body by this angle about that particular axis, then the mass distribution does not change. So, we can take some simple examples. For example, suppose you have a square plate or this plate, this rectangular plate, and then I have a line which passes through the center of this rectangular plate and is going in perpendicular direction. Okay. So, now let me put it on the table. So, now see the mass distribution, where the masses are, where this rectangular plate is. Suppose I rotate it by an angle pi by 2, rotate pi by 2 about this z axis, about this chalk, the mass distribution has changed. But if I rotate it by an angle of pi, so I come here, and if it is a uniform plate, I get the same mass distribution again. Mass distribution now and then the mass distribution now is the same, identical if the plate is uniform. So, this axis is such that a rotation of 2 pi by 2, a rotation of 2 pi by 2 which is pi about this axis does not change the mass distribution. So, this axis is a two-fold rotational symmetry axis. Similarly, suppose you have a triangular plate, equilateral triangular plate, and you are at the centroid, and then draw a line perpendicular to the plane, rotate by 2 pi by 3, 120 degrees. Now, look at this object. If I check for this axis of rotation, this line through the center, and see the mass distribution now. This blade is here, this blade is here, this blade is here. I rotate this fan by 120 degrees, 120 degrees. The same mass distribution, I have obtained. Another 2 pi by 3 is this, the same mass distribution I have obtained. Another 2 pi by 3 and I get the same mass distribution, and this time I have completed 2 pi rotation. So, the same particles have returned to the same positions. Okay. So, I am not worried about that. If the mass distribution is same, 2 pi by 3, rotate by 2 pi by 3, and you see that the same mass distribution results, this is a three-fold rotational symmetry axis. Now, here is a square plate, this is a square plate, and suppose I put my axis here through the center perpendicular to the plane of the plate. Now, you can very well see, if I rotate this plate about this axis by 90 degrees, that is 2 pi by 4. So, 90 degrees, I rotate it by 90 degrees, and you see that you get back the same mass distribution. Rotate by 90 degrees and you get the same mass distribution. Rotate by 2 pi by 4 and you get the same mass distribution. So, this axis is a four-fold symmetry axis, rotational symmetry axis for this plate. Of course, this 4-fold, if you rotate by 2 pi by 2, that is pi, right, then also you get the same mass distribution, but it is not called 2-fold symmetry axis, it is called 4-fold symmetry axis. All right. So, if a rotation of 2 pi by n with n greater than 1, it has to be positive integer and also greater than 1, because if it is 1, you rotate by 2 pi, so everything will get back to the same position. So, that is not a rotational symmetry axis. If a rotation of 2 pi by n with n greater than 1 about the axis, about the line, does not change the mass distribution, of the body, this axis or this line or this direction is called n-fold rotational symmetry axis. And is, this is important for us, is a principal axis, of this object, of this body, through any origin on this line, on this axis. Okay. So, if I have an object and that object, and then there is a point, and I can find a line, which is 2-fold symmetry axis or 3-fold symmetry axis or 6-fold symmetry axis, this line has to be a principal axis through this origin. And if I take my origin here, then also, if I take my origin here, then also. So, this line is a principal axis of this object. So, this is one way to guess the principal axis. If you recall our calculations, I said that this is not a principal axis, If I am using this as x, this as y, then I rotate it along about this line, or if I rotate it about this line, my angular momentum is not parallel to the angular velocity, but if I rotate it about this vertical line, then it is, and I said that this is a principal axis. But is this a rotational symmetry axis? No. If you rotate about this line, you will have to rotate all the way 2 pi rotation, then only you will get back the same mass distribution. You have to rotate it all the way 2 pi, then only you will get the same mass distribution. So, it is a principal axis, we have seen that in the calculations, but not because of this. There is yet another beautiful way. If that symmetry also exists, you can get the principal axis, and that is when you have what you call plane of reflection symmetry. If you get a plane through the point of interest, and so that if you reflect the body in that plane, the mass distribution does not change. That plane is known as plane of reflection symmetry. So, if the object is reflected, okay, in the plane, and the mass distribution does not change, that plane is known as plane of reflection symmetry. Let us take examples and look at this brick here placed on the table, and let me take a plane. Suppose from the middle I am using this plane. What happens if I reflect this brick in this plane? This side will go to that side and that side will come to this side. Everywhere all particles have to be reflected. These particles will go that side, those particles will come this side. So, the mass distribution will remain the same. Of course, the brick is supposed to be uniform. So, this is a plane of reflection symmetry. This is a plane of reflection symmetry, or this is a plane of reflection symmetry. This upper part goes to the lower part comes to the upper part. If it is right from the middle, these are planes of reflection symmetry. Similarly, if you consider this hemisphere, and then you draw a plane like this or this or this or this plane is plane of reflection symmetry. So, if the object is reflected in the plane and the mass distribution does not change, that plane is known as plane of reflection symmetry. And for us the most important thing is all directions or all lines perpendicular to a plane of reflection symmetry are principal directions or principal axis all such lines are principal axis. Okay. So, come back to this hemisphere, and I have a plane of reflection symmetry. You can see this is a plane of reflection symmetry. Now, any line perpendicular to this, that means if I draw a line from here perpendicular to this plane, this is a principal axis for this hemisphere. Okay. I am drawing tangent from this topmost point of this hemisphere, and this line is a principal direction, and in fact all tangents will be principal directions. So, this is another rule. If you can find a plane of reflection symmetry, then all directions perpendicular to that plane will give you the principal axis. Now, if I talk of my rectangular plate, the example with which I had done all the calculations, is a two-dimensional object. So, this plane itself is a plane of reflection symmetry. Okay. Here are the masses, these are the masses of the object. If I reflect this object in this plane, what happens? Nothing happens, everything remains at its own position. So, this plane itself can be called plane of reflection symmetry. So, all directions which are perpendicular to this are principal directions, and that is why this direction, that is why this z axis is a principal axis. So, if you can find a n-fold rotational symmetry axis n greater than 1, that will be a principal axis. Through all the points, origin can be taken anywhere on that particular line, that will be principal axis. If you can find a plane of reflection symmetry, then also it is very simple. Any point you take on that plane and draw a perpendicular line, that will be principal axis. So, you can identify the principal axis easily if such symmetries exist, and if you can, then you can write your equations which take very simple form.